Hello, this video is section 7.2 from the Larson book, hypothesis testing for the mean. Population standard deviation is known. So this will be similar to when we did confidence intervals for population standard deviation known, meaning that these will involve the z values. All right, the end of 7.1 had this rule right here, and then we're just starting off this section with it also. And so to refresh our memory on this here, that the decision rule, and when we say decision rule, we mean deciding on whether or not we're going to reject the null hypothesis. That's what we mean. So the decision rule to reject or not is you compare the p-value with the given level of the alpha. If the p-value is less than or equal to alpha, and remember that alpha is also called the level of significance, same thing, less than or equal to alpha, then reject the hoe. If the p-value is greater than alpha, then fail to reject the hoe. So it's pretty straightforward. Here's an example. Suppose we want to find a p-value for a two-tailed test with a test statistic negative 1.72. So as we learned in the last section, two-tailed test, the test statistic may be positive or negative, but so it will automatically cover both ends, both sides of this. So all we have to do is find the area left of negative 1.72 and multiply it by 2. So using Excel, we could just say equal 2 times norm s dist negative 1.72 comma true. True being cumulative, it will give you, so without the 2, it'll just give you this section by itself, which is 0.427 multiplied by 2, you get the 0.854. And in the calculator, you would use normal CDF. You would go 2 times normal CDF. The negative 1e to the 99 represents negative infinity to negative 1.72, and then it has 0 and 1 there, meaning that's the mean and standard deviation for the z distribution. And you see it's 0.0854. Now let's say we have this p-value and deciding whether or not to reject here based on a couple different level significance. So suppose your level significance was 0.05. So you put your p-value on the left, 0.0854, your alpha on the right, 0.5. In this case, the p-value would be greater than the alpha, and therefore we fail to reject the hoe. Now if alpha is 0.10, 0.854 would actually be less than or equal to 0.10, and we reject 80. Many statisticians would kind of be frustrated with this result a little bit, because you kind of want to either be clearly reject, but if it's not, you want it to be clearly not reject. It's the fact that it can wedge in there between a couple of these numbers makes it a little, they like, but especially if you're looking for reject, you want a really, really small p-value. Now these p-values are probabilities, so they are numbers between 0 and 1. So we say small, like 0.0001. That would be a small p-value, and that would be good if you were looking for reject. It would clearly be reject. So some people, like I said, confuse these by thinking high p-value is rejection. No, that's wrong. It's low p-value. So here's just a little slogan that came from a different book, and I like it. It says, if the p-value is low, then the hoe must go. So there you go. We'll get rid of the hoe. And yeah, so low p-values is what leads to rejection. All right. Z-test for the mean. So in the last time, the 7.1, we mentioned something called a test statistic, and we had some issues where it gave you the test statistic, but this is the first time we are seeing the formula that calculates it based on having data. We just worked with the idea of it, like we did. Well, like for example, right up here, we did the same thing. You know, this here's telling you what the test statistic is, but here's how you get it if you have data. Now you're not going to need this formula. Now there's two methods when performing a z-test. You can use p-values, or you can use what's called rejection regions and critical values. So we're going to start off by using p-values first. Then we'll get to the second part a little bit later. So we'll look at some examples of, let me get this on the screen here a little bit, okay. All right, so let's say we've got, all right, so you've got a distributor reports an average 150 sales per day for that distributorship. You suspect this average is not correct. So you select 35 days, determine the sales each day, and the sample mean for those days was 143, and the population standard deviation is 15. Given a level of significance of 0.01, is there enough evidence to doubt the disputer's reported average? So the way we look at this, so actually, is we look at this, you know, from the point of view that we're doing the testing here. So you're saying that you suspect this average is not correct. So is not translates to not equal. And we talked about some of those. We had those phrases I had in the section 7.1 that kind of showed you some of the wording based on that. So is not, so we have not equal right here, and then that's your claim. And going back to those three rules in the previous section, not equal for the ha automatically pairs up with equal for the ho. That's in fact, this is a two-tailed test, but it has to be equal for the ho, and not because we have not equal already for the ha. Not equal can, you know, not equal can never be the ho. So let's put this in the calculator. I've got it right there, but let's you can watch it in real time here. Okay, let's bring this. Okay, so to do this, we go to Stat, Test, Z-Test. Now, in this chapter, I want to make something perfectly clear here. If you're a calculator user, anything involving these hypothesis tests, the function will be test. See, now we've used, I'll scroll down here and show you, for confidence intervals, Z interval, T interval, and then we used one prop Z interval. We've used those three from the other chapter. So that's the way you tell the difference. It's pretty straightforward. So interval, if it has interval in the title, it means confidence interval. If it has test, it means hypothesis test. Because I've had students before, especially like in face-to-face classes, they'll, why does this not look right? You know, when they come up and they'll bring it to me and show me what they've done, and it's because usually like this, you know, they picked, instead of Z test, they picked Z interval. All right. Now we want stats here because we're going to be entering in the values. Stats means you're entering the numbers, just like it would before. Now the mu0 is what we're testing here, the value we're testing. That's what the fancy term for that is called hypothesized mean, but we don't need that fancy term. It's 150. Population standard deviation is 15. The actual average of the sample is 143. Sample size N is 35. And here's the very important part of this if you're doing the calculator. You have to choose which one of these three things to pick, and they only have the alternative hypothesis there. We really didn't need both. All you have to do is pick one of them. The first one is for two-tailed. The middle one that's highlighted in the screen now, that's left-tailed, and then the one on the right is right-tailed. So it's based on the ha here. So you see ours is a not equal, so I hit enter there, so you see what happens. That one's now darkened, and that's what we want. Very important, because you will not get the correct p-value if you pick the wrong one of those three. And then there we have the results. So I'll scroll down here. There they are in the calculator. So see, I labeled it right here that you have to pick the correct ha for this. And there you go. There's the test statistic if it was asking for that. The p-value, 0.0058. And you have to be careful with these. I believe I mentioned that in 7.1, but if I didn't, I'm happy to say it again, is that if you move the decimals over, it's tricky because you see that 5 is bigger than 1, but actually the extra 0 makes it smaller. Now, I was just, last section like I showed you about moving the decimal places over, but you could, since this one has 4 decimal places, if I multiply this number by 10,000, I take 0.01, and this is only if you're having trouble to tell which is smaller than the other, but it's got to be the same number here, 10,000. So now it's like comparing 58 to 100. Then you easily would know, oh, okay, 58's less than 100, so I have the arrow going the correct way. But that's only if you need to do that. But it can be kind of tricky because you see, you got to be careful because the extra 0 does make it smaller. All right, so what does that tell us? P-value less than alpha, that means reject. Therefore, and the claim is the alternative, so therefore we reject the hoe. We reject the hoe, and we support the claim that the mean sales per day is not 150. We agree with that. There we go. Now in Excel, we have, I already have the file open, but let me just show you. And I'm sure you would have noticed it when you were doing confidence intervals. But right next to the file where the confidence interval Excel file is, we have and right there at the bottom, calculating hypothesis test values. But I've already got it open, so I won't open it from here. So here it is, the file. Now we're working with this one mean z distribution. All right. So what you have to do, the calculator, you had to pick the right symbol, either not equal, less than, greater than. Here you pick it by wording. Now be very, very careful, because I've even not paying careful attention, picked the wrong one. So there's 3 of these, you see. So you got to enter the numbers in the right one. Ours is a two-tailed test. I believe we have 0.01. If I remember, I can double check these numbers, obviously. Sample mean, I believe, was 143. The hypothesized mean that we're testing against is 150. Standard deviation, I forgot that one. I believe the sample size was 35, but I forgot. There it is, 15. Yeah, 15 and 35. And there's your p-value, 0.0058, rounded. And then we'll need these critical values. There's the test statistic, if it's asking for that. So there you go. So you just have to make sure. So it's a little more challenging than confidence intervals because you're having to pick the right one of these 3 formulas to use. So just be very careful. And then there it is, same things I just entered right there. And you can see I copied the two-tailed z-test, so you know. Alrighty, let's see what we got here. Manufacturer system, sprinkler system designed for fire protection claims that the average activating temperature is at least 135 degrees. To test this claim, you randomly select a sample of 32 systems and find the mean activation temp to be 133 degrees Fahrenheit with a population standard deviation of 3.3 degrees Fahrenheit. Given a level significance of 0.10, do you have enough evidence to reject the claim? Now, let's be careful. Let's see how we set up the ho and the ha here. Claims is at least 135. At least, symbolically, is greater than or equal to. Greater than or equal to is always a ho, because it has equal in it, and its partner in crime is always less than. By that, so therefore that's also a left tail test. But this time the claim is the ho. They're claiming that it's greater than or equal to 35. So let's test this. So it's a left tail test. And you see the direction of your ha. That's going to be important in the calculator. So we go stat. Oh, well, turn it back on here. Stat, test, z-test. We're testing against 135. Population standard deviation is 3.3. Sample mean is 133. Sample size is, we're at 32. There it is. Now, okay, watch carefully. See, I'm picking the middle one, the less than, because our ha is less than. And once I do that correctly, hit calculate. Okay, this negative 4, that's just scientific notation. That means if you were to take the decimal and move it back 4 places to the left, that would put 3 zeros in front of that number. So it's really, I wish I could find some way to make it not show it, but it's 0.0003. Now Excel should show it that way. Well, I say that. I don't want to speak out of turn. It may also show scientific notation. But here, you see I wrote, no, okay, there it is in Excel. There it is, 0003. All right, now to do this correctly in Excel, we have to pay careful attention and pick the correct one of the 3 to use. This is a left tail. I already forgot the level of significance. I'll have to go back. 133 was the sample mean. 135, I believe that was 3.2. I'll double check that. That doesn't feel right. I'm thinking now it's 3.3, but I'm going to go look anyway because I need the level of significance. So I'll check that in the standard deviation. 0.1 is the level of significance, and it's 3.3. Okay. Okay, so the level of significance just happens to be already correct in there at 0.1. I didn't have to change that. So you see here's the p-value right there, 0.0003. And there it is. Now p-value clearly 0.0003 is going to be smaller than 0.10, and therefore we reject the claim that the activating temperature is at least 135 degrees. So we're rejecting that ho. All right, and here we got some other, let's see, what do we got here? 8th grade, 85 8th grade students, some sort of math test here. 282 is the mean. Population standard deviation 35. The state school administrator is declaring that the mean score for the state's 8th graders in the exam is more than 275. Level of significance of 0.04. Is there enough evidence to support their claim? All right, so here's the key thing. We got to get the ho and the ha set up. More than 175. See, that's different than the last problem where it said at least. At least means greater than or equal to, but more than is just greater than. So here's your claim. And then the ho, the opposite of greater than, makes the ho less than or equal to. And then by definition of these symbols, that is called a right-tailed test. And where it says enough evidence to support the claim, so what's going to happen to support this claim will happen if we reject the ho. Then, because rejecting the ho means we prefer the alternative, and that in this case, that's the claim. See, one thing I'll mention about this hypothesis testing, you never can really support the claim if the claim is the ho. The best you can do is not really support it, you just don't reject it. You just don't dispute it. Yeah, we've talked about that in 7.1. It's kind of a little tricky, I think, on the meaning on that, but this is much stronger if your claim is the alternative and you reject the ho in favor of that. That's a much more powerful result. All right, so there are our numbers. Let's go to the calculator. All right, so I brought the calculator back up. I accidentally exited out, so I don't want to waste any time opening that up, so I paused the video. And z-test. So we're testing this against 275. Our population standard deviation is 35. Sample means 282. And it's 85 8th graders. Okay, here's the key. This is a right-tailed test, meaning the alternative is greater than, so we hit greater than right there. And let's scroll down and see if that's what we had before. Well, calculator. I'm not sure why I had that normal curve there, but so let's see. Now you can look at the screen on the left and look at this screen right here. Okay, that looks good. So there's our p-value, and so we can put this in Excel real easily. Just we have to come down here to right-tailed test. Yeah, so whether it's the calculator or Excel, you still have to make a choice here, on which one of the three to use. Sample mean, I think was 282. 275. Standard deviation, I think, is 35. N is 85. That'll be a miracle if I remembered all that correctly. Ah, it's a miracle. And then there we go. So same p-value. And what kind of conclusion do we reach here? .0326 is less than 0.04. So we reject the ho, and we support the administrator's claim because the claim was the ha. We respect it, reject and support that claim that the mean test score is 275. So we agree with that based on this sample. And just to remind you, that level significance alpha, that's the probability of making a type 1 error. So in this case, there's a 4% chance that we've rejected it falsely, in other words, that we're incorrect. All right, this is kind of a it's testing, it's giving you a p-value, and it's just testing against 3 different alphas, and then do you reject or not reject just one at a time. So for example, the first one, you look at 0.036 and 0.10. Well, 0.036 is less than 0.10. I'm gonna, okay, I can't, all right, I can't write very well with this mouse pad, but I can once I get it in handwriting form there. So I can say that 0.036 is less than 0.10, and then 0.036, and you'll be able to see this and display here when I finish. Then I'll show you what we and 0.036 this time though is greater than 0.01. Make it a little bit bigger here. Okay, so you see you're comparing that 0.036 to each of those given alphas. So when the p-value is less than alpha, we reject. So you see the first one's a reject, the second one is a reject, but the third one is fail to reject. So the answers yes or no are based on rejecting, because it says, can you conclude that it should be rejected? So first one's yes, reject. Second one's yes, reject. Third one is no, don't reject. So that is why yes, yes, no would be the correct answer choice for all 3 of those. So you're just comparing it to each level of significance. I think I might just leave that there. Now let's look at the critical value method and see what that's all about. So no longer using p-values when we are going to be using them, but we're learning something new. We'll be able to use both here. So now these critical values, and I can show you how to get them in the calculator, and they'll be easy to get off that Excel thing, so we don't have to worry about using the normal chart. Let me just kind of show you what they are. See, so instead of, on the p-value, when you use the value on the x-axis here, and we saw that in the last section, that's your test statistic, and your p-value is the area under the curve. But what this is, the area under the curve is actually your alpha, your level of significance. Then the z-value then, so it's sort of like an inverse norm process in a way. So your inverse norm will get you whatever that z is right there. Okay. So, and then the right tail is going to be on the right side. So it'll be a positive over on this side. And then two-tailed always has 2 critical values. Sometimes in problems it'll say critical value or values plural separate by comma. So if it's two-tailed, you would have 2 of them. It probably will tell you to put one of them comma the other one. And then half of the alphas in each end. So if alpha was 0.05, you have 0.025 in each end there. Actually, I'll show you how to do these in the inverse norm, the calculator. Now these shaded areas, which represent the alphas or either alpha over 2, is what's called the rejection region. And then the z values with the alpha are alpha over 2. Those are your critical values. So what happens is if your test statistic, your calculated test statistic, if it's a number that falls in the red part, and for any of these, if it falls in the red part, the hoe is to be rejected. If it falls anywhere on the other side, it's not reject. So that's why it's called a rejection region. The shading is where you reject. Now, of course, in a two-tailed, the number's not going to fall in both places. But if it's in one end or the other, that's good enough to be reject. All right. So here are the decision rules, the wording for decision rules for the test. So, with p-values, it was just comparing the p-value to alpha. That was it. But this one, the wording looks like this. For left-tailed, our wording says, reject the hoe if z is less than the negative z alpha value. Right-tailed says, reject the hoe if z is greater than the z alpha. And two-tailed, you always have an or. Reject the hoe if z is less than negative z alpha over 2, or z is greater than z alpha over 2. So I don't know if we're going to have a homework problem in this thing or not that does this, but they put the word and in there instead of or. Just treat it as or, because and is not right, because and means they would both have to be true. So just ignore anytime you see and. That's just a mistake. I can't really correct it. All right. Now, I'll show you how to do these. Like I said, we'll just look at a critical value example right now. And I'm saying I'm using 0.03 as an example. Now, if it's left-tailed, it's going to be the area over here to the right. I've got the calculator screenshots down the page there, so you'll see them again. Second distribution, inverse norm, clear that, 0.03. This will be how you do it for a left-tailed test. Negative 1.88. Now for a right-tailed test, the answer is actually going to be the positive of this number, but just to show you, because you might only be wanting to do the right-tailed test. You could do it as a left and then just make it positive if you want. But here's how you do it directly. What you have to do to get the number directly is you have to treat, because if that's 0.03 out here, the area to the left would be 1 minus 0.03. So for these right-tailed, if you put 1 minus 0.03, but look, so as promised, it was just the positive of the other answer. Now, two-tailed, it's not going to be these same numbers. It'll definitely be different numbers. Because it's half the area, we're going to find the negative number, but then we're just going to go with the knowledge that there's also the positive number. You don't need to find both. Once you have the negative, you have both of them. So this one, we go inverse norm again. And you go 0.03 divided by 2. That will give me the left value for, so that means there's two of them though for this automatically, negative 2.17 and positive 2.17. Let's see what I had down here. There we go. And I wrote it out in words, that therefore, you only need to calculate one of them for the two-tailed, but know that there's both. There's the negative and the positive. Because you see how this decision rule looks. That decision rule, is expecting two numbers here. All right. You know what? I did it this way in Excel. I'll leave that there. I'm not going to go back, and I went ahead and just did the absolute value of that one just to get the positive. But let me just show you what else, what you can really just do instead of doing all that is just put it, because the other numbers do not matter. Because watch this, I'll put in 0.03, and there's my critical value right there. I put in 0.03 here. There's the critical value, positive 1.88. So you didn't. I don't know why I did it that way in the notes. That's okay. It's obviously correct. But see, because the other values, we don't, to get the critical value, all you got to do is, but whether it's left-tailed, right-tailed, or two-tailed, just tell it the level of significance, and it'll give you this critical value right here. That'd probably be quicker. And then put in 0.03. And I wrote this, I set this up for you to when it's already got both critical values there. So negative 2.17, positive 2.17. So if you like what I did in the notes like that, you can just do that, or just go to the already spreadsheet that we have there. Because that's exactly, these commands are exactly how I'm calculating these on that spreadsheet, so there's nothing really magical there. So, all right. So now we're just looking up how to write decision rules, just practicing how to write the appropriate decision rule using critical values and rejection regions. So this is left-tailed, alpha's 0.01. So if you just do an inverse norm of 0.01, that'll get you your value. And it always, for a left-tailed test, it's always phrased like this: reject the hoe if z is less than whatever the number is. In this case, negative 2.327. This one says right-tailed 0.10. Now this, of course, you can inverse norm, or you can get these off of, did I put the Excel? I don't know, but I did the calculator, but I can do the Excel real quick if you want me to, but I think that's pretty, as far as just going to the spreadsheet, that's easy enough, but I'll do it real quick. But I definitely wanted to show the calculator for people that are using it. Right-tailed, 0.10. Right-tailed, you have to go 1 minus the value. So 1 minus 0.1, 1.28, 2 roughly. So you'd reject the hoe if your test statistic z was greater than 1.282. So a right-tailed test is always phrased as greater than. Two-tailed, just put in 0.05 inverse norm divided by 2, so it's only going to give you the negative, and we just know that there's a positive that goes with it. So the proper wording for this is reject the hoe if z is less than negative 1.96 or z is greater than positive 1.96. So I guess it won't take but a second. I'm not going to copy anything from Excel over to the notes, but I can come in here and do left-tailed 0.01. And there's the negative 2.333. I believe this one was 0.10. There's 1.28. And the two-tailed, I think, was 0.05, but I'll type it because I know the answers. I think so. Yeah, negative 1.96, positive 1.96. And I believe so. So there we go. So yeah, you could just do those in Excel. All right, so let's try a hypothesis test problem. And using critical values. Now, one thing I'll mention before we do these, in case you were wondering if this came to mind or not, you can wonder, well, if you do a hypothesis test by p-value and critical value method, is it possible that you could reach two different conclusions? Could you get reject by one method and not reject by the other? No, only if you make a mistake, only if it's done incorrectly. They have to reach the same conclusion. Either method would, if it's supposed to reject, both methods lead to reject. If it's failed to reject, they both better yield fail to reject. So if you did it two ways and got two different reasons, one of the two methods is done wrong then. So just thought I'd throw that in there. Okay, claim the mean workday of firm office staff is more than 8.5. Okay, I don't like to get tricky on the wording. I'm not really trying to, my goal is not to trick you here by any means, but more than means greater than. Greater than means ha. So that's our claim right there. And this always pairs up with less than or equal. So I just kind of wrote the sample statistics right there. And you can see to get the critical value, there's the inverse norm result, and there's if you do this, but remember, you can just put this in the spreadsheet and just, what is it, so 0.01 right-tailed test. You don't have to use that command I used right there, but so if I go right here, wait, what did I do wrong here? And there it is, 2.326. So we have 327, whatever. I don't know why I put 7. I probably should have put 6 there. I might have got this off of a chart and didn't. I guess I could change it while I'm here. All right. So our decision rule using critical values is we're going to reject that hoe if the test statistic is greater than 2.326. So it's a right tail test. So in the calculator, all right, let me get, and I'll be careful not to hit the X this time. Yay! I didn't exit out. I didn't close the calculator this time. Good for me. Stat. Test. Z-test. Stats. The mu0 that we're testing against, 8.5. Standard deviation, 0.5. 8.8 is the sample mean. Um, 35 is in, and then this is a right-tailed tail. Okay, so the correct one there is already highlighted, the greater than. That's correct. So there's our test statistic. Our test statistic roughly is two places is 3.55. So I kind of drew a little visual for you there. You can see that the test statistic falls, so the rejection region's anywhere, to the right of 2.327, so 3.55 would fit in that region. Therefore, it's reject. In Excel, I think I'll just leave this here. I won't type this one in because, like I said, you'll see it in the homework in a minute. But, okay, pretty straightforward. But you see the key is I picked the right-tailed test, entered the values in there, and there you go. There's the same critical value. I don't know, I should have highlighted the test statistic, but there it is, 3.55. I don't know why I didn't highlight it. I highlighted the p-value. So since 3.55 is greater than 2.33, we reject the null hypothesis and we support the claim, because the claim is the ha, that the mean workday is more than 8.5 hours. Now, one thing I'll mention about this problem is if you look, if you did look at the p-value, you can see that p-value is pretty small, 0.0019, yeah, and that would be less than alpha. So like I was saying earlier, it's got to reach the same conclusion by either method. So you would definitely reject also by p-value. Although that wasn't the purpose of this exercise, but just always like to kind of throw that in there. Okay. How many more of these? I don't know. We'll probably get to the homework here pretty soon. I may leave one or two of these ones that are here undone. I mean, not completed because, yeah, we don't need to do all of these. I mean, they're obviously going to stay in the notes if you need to look at them for examples, but I think we'll just do a couple more and let's move on to the homework. As I found, since when I'm teaching, especially like face-to-face classes, since I've started, but we've been using the homework in other stats classes that I teach. Yeah, I find that I have probably too many examples in my notes to have time to work them all out. So I don't work them all out in a regular class because I jump into the homework. But back in the olden days, it was good to have this many examples to show students. But then I just leave them there, so you still have them, and you can always ask me about them. All right, coffee shop claims its fresh brewed drinks have mean content, caffeine content of 140 milligrams per cup. And you want to test this claim? You find that a sample of 42 cups has a mean caffeine content of 146 milligrams and a population standard deviation of 22 milligrams. At the level of significance of 0.05, do you have enough evidence to reject the shop's claim using rejection regions? All right, so mean caffeine content of 140 milligrams per cup. So just treat of sort of like is, it means equal. Don't try to read anything more to that, like is that more than that or less than that? It means equal. So we have equal paired with not equal. The claim is equal here, by the way. And then this two-tailed test, of course. Now there's the calculator inverse norm, how you would get your critical value. Now keep in mind this does, because it's two-tailed, it has two of them. So but you only need to make one calculation, because if negative 1.96 is one of them, positive 1.96 will be the other. And you can either use this norm inverse, or you can just put it in the spreadsheet like I showed you before, put the critical value with no other numbers in there, and then it'll show you the critical value. It actually shows you both. So might as well do it. Well, it's already right there. There to 0.05, and here they are, both of them. Negative 1.96, positive 1.96. All right, so let's see what we have here. And that means we're going to reject the hoe. So this is the wording when it's two-tailed. If the z, the test statistic z, is less than negative 1.96, or if it's greater than positive 1.96. All right, so, and, okay, I'll save a little time by not retyping this one in there at least anyway. Stats, so 140 is your hypothesized mean, 22, standard deviation, 146 is the sample mean, 42 is your sample size, and then of course you have to pick the equal here. And there's your test statistic, roughly about 1.77. Now I just kind of drew the shading there. I think that may help a little bit to kind of see tell better where the number fits. And you can see, well, obviously it would have to fall, it can't fall on both shaded part, but the fact that it's positive means, is it bigger than the positive number on this side? And it's not. In other words, if the number falls kind of in the empty region, or falls in that part, that means do not reject. So it's in the not reject zone right there in the middle. And so in the spreadsheet, 0.05, Sample mean is 146. Hypothesized mean is 140. Population standard deviation is 22. Sample size is 42. Okay, there's your test statistic Z. I have the p-value there earlier. I should probably go back and edit the notes and fix this one real quick. I might do that to where I can at least highlight all three, but the test statistic for sure needs to be highlighted because that's the method we're using. All right, so we failed to reject the null hypothesis, and we don't have enough evidence to reject the claim that the mean caffeine content is equal to 140. So once again, I know I keep saying this a lot, but because it can be confusing, that's why. So we're failing to reject the null hypothesis, and that was the claim. We don't have enough evidence to reject it, but that doesn't mean we support it. Like I said before, you can only support a claim if it's the alternative and you're rejecting the whole to support it. Here it just means we don't reject it, but we don't love it either. All right, well, I don't know. I think I might. Let's see. I'm trying to decide if I should do this one before. I don't know. I think I'll go ahead and just jump into the homework if that's okay with you. I guess nobody's going to actually answer that, are they? But these examples will stay there. I'll just show you one thing about this one on the graph. I'll explain this real quick. Because sometimes it can be confusing to tell, if one negative number is bigger than another negative number. That can be a little confusing. So you can take this graph and you can flip everything over to the other side, and then therefore that way you would know for sure that 1.29 is not greater than 1.645. But sometimes it's trickier on this negative side. So that's all I'm doing in that picture right there, is showing that. Okay, so yeah, there's just a couple more examples. I mean, certainly worth your time to look at those for sure, but I think I'll go ahead and move on to the homework now. So here we are. I may skip over some of these and okay, it looks like here's one where this is like that one I showed you in the notes where I typed in, where you're comparing this p-value to 3 different other alphas. Yeah, that's exactly like that one I did in the notes. I'll leave that one alone. And so for a p-value, so this one goes back to what I showed at the very beginning of the section, where it's already giving you the test statistic. How do we get the p-value? And it all depends on what kind of test it is. It's a left-tailed test. Because if it was a two-tailed test, we would have to get the area to the left and double it. So this one, calculator. Now in Excel, we won't be able to use the spreadsheet. We'll have to use that norm function there, norm S distribution, because the spreadsheet, though, it's based on entering data. It's not based on already knowing what the test statistic is. So I'm going to go, like I said, we only multiply it by 2 whenever it's two-tailed. Normal CDF. Okay, this is less than, so that's where I want it to start, right there. The upper will be negative 1.88. 0 and 1 are fine. It wants 4 decimal places, so I'm going to go 0, 3, 0, 1. Got it. Now let me show you the Excel command, though. I guess I can just do this and I can bring up a new. All right, so I'll put it here, and then I'll do the formula. Well, I'll put the formula text in there. Nothing will be there yet, but B1 and I'm going to put equal norm. I can type here. Norm S for standard normal distribution. Dist. The value was negative 1.88. So you can only do it this particular way whenever it's left-tailed. Right-tailed, you'd have to do 1 minus norm dist, and it would be positive. Oh, there it is. So there it is, 0, 3, 0, 1. You can always go back to that first section in chapter 5, finding area under the normal curve and all that kind of stuff, where we were using this norm S dist more back then. So 0, 3, 0, 1, that's going to be less than 0.05, and P less than alpha, we reject. Wonderful. Okay, this same kind of, I guess I should have, well, all right, two-tailed, I'll do this real quick. Two-tailed, negative 2.49. So I can go 2 times, or I can multiply by 2 at the end. Second, okay, I can do the same thing here. Just put in 2.49. What in the world did I hit? .49. So it should be 0.0128. Excellent. I can go back to that Excel sheet. Not our normal one here, but I can go put a 2 in front of this now. And then you'll see the formula when it spits out. And what was that, negative 2.49? I'll double check this, of course, but yeah, 0.128 sounds right, doesn't it? So I think I got that right. Yep, 0.128. 0.128 would be, p-value would be less than the alpha, 0.09. Reject. Fantastic. All right, so, okay, I'll skip some of these. Let's get to the which wants a critical value. All right, we did that. I can figure you can do that. Okay, let's jump ahead. Okay, now here's where we're actually doing a hypothesis test, looks like, so that's good. So we'll play around with a couple of these 2 or 3 of these at the end. Okay, here's the claim. Mu equals 30. Equals 30 has to be a hoe, but its partner has to be not equal. So you see there's 2 others that have equals for hoes, but they don't have not equal. They have less than or greater than, so wonderful. Standardized test statistic. Calculator. We'll do this thing again. Bring that back up. Slide this over. Much more efficient when I can look at the numbers, not have to toggle back and forth and try to remember them. That's not fun. And okay, stats. We're testing against 30. Standard deviation 3.39. Sample mean 28.6. N is 55. All right, so we know this is a two-tailed test. So we have to highlight that first one right there. Very important. That won't matter for test statistic, but it will for p-value. So, but you know, let's just do it right anyway. All right. Oh, what? I'm sorry, I messed up here. But everything's already going to be entered in there, so I can just bring it back. So the test statistic, it wants 2 decimal places, negative 3.06. Excellent. Critical value. Okay, this one words it. So this one it should say separate by comma, doesn't it? Or I mean, well, let's see what it does. We know because it's an equal, not equal, two-tailed, there's going to be 2 critical values. Oh, I always got the plus and minus in front. But sometimes problems will say it doesn't put the plus and minus in front. It just leaves the box there, and you would put in the negative one, comma, the positive one. So let's see. Now you can get the critical value here by doing norm, because I'm going to put this all in the Excel here in a second. If this one you want to do inverse norm to get critical value, not normal CDF. So critical value, the alpha is 0.02, but it's two-tailed, so I have to put 0.02 divided by 2. That will give me the negative number. It wants 2 decimal places. So you see it's got the plus and minus symbol already in there. So I'm going to put 2.33. And like I say, you could draw a normal curve if you wanted to. I'll just make an ugly looking sketch here. Freehand. I could at least copy it. That would help if I copied. Let's see. Go back. So I remember seeing that. Where was that normal curve I had sitting there that was already... Well, I can take any of these as long as I don't copy the values. Yeah. Should just take the graph. I didn't mean to do that. That doesn't matter. So the idea was the critical values are 2.33. So you'd have a negative 2.33 here. Yeah, see these are, why is it dragging that? Three. We got a positive 2.33. I tried to do the decimal. Okay, it's 2.33. It's not 2. Well, I better erase it. All right. So there's your rejection region. And then what was the test statistic? Is Negative 3.06. So, yeah, negative 3.06 would be to the left of, mess up every time I try to put the decimal there. Can't put a decimal there. Stop. Now I can't draw anything. And then now it's completely gone. Okay, all right, I'm not messing with this anymore. Okay, it's in the rejection region. It was, I think you saw enough there. It's reject. And the claim is the hoe, so we do reject the claim. Fantastic. So assume that we'll have one, let me just double check here that we'll have one with p-values. Okay, I just realized I moved away from that last problem and I had not done it in Excel. And because I went to check another problem, and when you go back, it gives you new numbers even if you've done the problem. But the good news is, if I come over here, because we just, wait, we didn't, no, we didn't put those, we just used the command to get the calculator. Okay, let's, this is the same problem, but it's got different numbers. I should have had, didn't I do this one in the calculator? How did I get the test statistic? Let me see what answer this spits out. Okay, that was it. Now I remember negative 3.06 being the, so if I bring this now, yeah, so I can just put these values in the spreadsheet, even though they're not in the problem anymore. And okay, so it was a two-tailed test. Alpha was, I don't remember what alpha was, but anyway, 0.02 sounds right for some reason. I don't know. Anyway, let me come back to that. Just okay. We're going to do it. We'll do this again with another problem. 28.6. Hypothesized mean was 30. Population standard deviation was 3.39. Sample size is 55. So there's the negative 3.062. Yeah, those weren't the critical values. I'm going to try 0.02 and see if that, maybe I'll recognize, because I accidentally deleted that sheet. Remember, I was trying to draw by hand here, and I erased everything I did. So I don't know what I had on that chart. So I'm going to put 02 here and see if that looks familiar. Were they? I think they might have been negative 2. Yeah, I think they were. Negative 2.33 and positive 2.33. So I think that was correct the way it was. So, all right, there it is in Excel. All right, made a mess out of that one, didn't I? So let's try the next one, because I was looking at the next one going, hey, I like that one. So, and oops, I forgot to do the last one in Excel. So I'll pay careful attention and do both here. This one. Oh, let me get rid of the show completed. Now I don't care if we get new numbers. Claim is greater than or equal to, so it would obviously have a ha then of less than. Test statistics, so let's, okay, I'm sitting here in the z-test right now. The mu zero is 1475. Standard deviation is 27. Sample mean, 1465. N is 27. And now this is a left-tailed test, less than, so we have to highlight the middle one. Let's put in our test statistic, 2 decimals, so negative 1.92. Okay. Now this one wants the p-values. The p-value is sitting right there for us. 3 decimal places, 0.27. And what's our alpha? Alpha's 0.08. So the p-value is less than the alpha. So we reject. And the claim, we've got to be careful here because the claim is actually the null hypothesis. So we're not supporting the claim this time. There is enough evidence to reject the claim. Yeah, if the claim would have been the alternative, we'd have said there's enough evidence to support it. We would have supported the claim if it was the ha, but the claim's the ho, so we don't support it. All right, let's take a look, maybe one more of these. See which one of these two I like better, not that it matters. Let me see if I can find. Let's see. What did we have? That was a left-tailed. This was a two-tailed. Let's see if there's a right-tailed in here. I did it again. I forgot to put this in Excel. What is the matter with me? Left-tailed test. Fortunately, the numbers should all be there, thanks to the calculator. So it was 0.08. Sample mean was 1465. 1475. Hypothesized mean, standard deviation is 27. And the sample size just happens to be 27. There's our p-value, 0.27. Okay, so there's the test statistic, negative 1.92. So, all right, we're all good there on that one. I was hoping one of these other ones might be a right tail. Hopefully I tried to alternate them as much as possible. That's a two-tailed, because it says is. Okay, let's do this one. This will be the last one. Yeah, if this was a long lecture, there's a lot of stuff in this section. Let's see. You claim blah blah blah. Company claims electricity consumption is more than 860 kilowatt hours. Okay, more than, it's greater than. Greater than. Oh, this was even highlighting what the claim is. Okay, that's interesting. I like that. But it's clearly this one. Okay, it's probably doing a critical value method this time. That's quite all right. So to get the critical value in the calculator, this is a right-tailed test. So if you go second distribution, inverse norm, 1 minus the number. For a right-tailed test, it'll be 1 minus the number being alpha. And it says alpha is 0.10. Okay. Beautiful. How about 1.28? I see. We had one like that earlier. That was a two-tailed. Critical value is, so there's just only one of them, critical value for this. Excellent. Look at us go. So right tail test means you'll be rejecting to the right. So it has to be that one. Test statistic. So let's come in here. Z-test. The mu0 is, we're testing against 860. And population standard deviation is 128. Sample mean is 900. And sample size, 62 residential customers. This is a right tail test. So I need to pick the one on the far right here, greater than. Calculate. Test statistic. 2.46. Well done. Let's put this in the Excel. And it's right tail test. Always keep forgetting the alpha. 0.10. 0.10. Sample means 900. 862, I believe, was that number. Standard deviation. It doesn't show it there, so I got to go back to where we entered them. Oh, it's 128. No, 860, not 862. Wait. Yeah. Sample means 900. All right, we're fixing it up here. Standard deviation is 128. Sample size 62. And then so there's our 2.46 test statistic. There's the p-value. Then also there's the critical value. Okay. So let's see what we have. All right, so the 2.46 is going to be greater than the 1.28. So that number would lie in the rejection region. But you know, you can also verify the answer is going to be reject by the p-value. The p-value is less than alpha, so it's definitely going to be reject. But this is the right wording. The test statistic, to reject, it's got to be in the rejection region. Answer D makes no sense. You wouldn't reject something that was not in the rejection region, so that would never be the answer. So you reject it, that it's not in the rejection region. So fantastic. Okay, I think that concludes this video. Oh, what? Excuse me. There is enough evidence to wait. The claim was, let me double. I think we're going to support this claim because it was the ha. Yeah, see, the claim was the alternative. So we're going to support this. is greater than the 860. We support that claim. Is that it? Okay, that's it. All right, now we'll conclude this video on 7.2, hypothesis testing for the mean population standard deviation known.